Mathematics. Let's do it. Okay. Good morning. Hey, Rippy. Does this bring back good memories? Products of abelian groups. Oh, I'll take it. That was not a hard part of that class. Just breaking things down into... Fair enough. I'm glad that I give you so many positive emotions. That sounds healthy. Yeah. Seems like a good way to do things. Cool. So metric spaces. Fun stuff. I was randomly listening to Avril Lavigne last night, and I found that I have no idea what I'm doing with my life right now. I don't think I've listened to her in like a decade at least. But I grew up playing Diablo 1 while listening to Skater Boy. Oh, hey, physics. One of my few Hearthstone acquaintances who's here for the math, you know? By the way, Nick, I don't know if you read what I wrote on Discord. I don't know if that's like what you meant at all, because like the set notation like looked weird. But if that is what you meant, then that actually would work. But I'm not sure if it was or not. We can. Okay, then yeah. Okay, yeah, we can talk about that when we get to that problem. The key is that the smaller ball is closed, and so you're actually taking away a closed set, and so it's still open. Right, because you want like strictly greater than A, so you're going to take away the boundary. Yep. Okay, so I think we are ready to go. So yeah, we're going to focus, this is going to be pretty brief on metric spaces in all honesty. As I said, this is something you probably see much more in depth. Probably one more in depth if we were not doing kind of an IBL structure and we had more time, but also you'd see much more in depth in analysis where almost everything that you're dealing with are metric spaces. And so here we're really just trying to show that what we did with R2 when we were talking about open balls and stuff really was very generalizable, and that it really wasn't that special to R2. It was really the fact that we had a notion of distance. Okay, so that's the key thing. So first we need to know like what is a metric, right? Just because right, we're going to overlap with a little bit of what you were supposed to do for Tuesday, just because we kind of ran out of time with the quotient stuff. So, usually you'll see D for distance, and you're taking in two things from your space, right? And you're always spitting out a real number, and, sometimes you'll see it as R greater than or equal to 0 as well. It kind of depends on how you want to view things. Sometimes topologically it's more useful, it's whether you just want to like throw this subspace topology on this or just consider R in general and realize that things less than 0 are going to give you an empty pre-image, just kind of personal preference, really. But, to be a metric, right, we are requiring that the distance is always a non-negative thing, which makes sense, and has to be equal to 0 if and only if you're talking about the same point, right? So different points have a positive distance from each other. Of course, we would like distance to be symmetric. That's terrifying for all x and y and x. And then the last one is, so usually those two are like super fast to verify, right? Especially in the examples you saw. I know I didn't require you to show that all of those guys were metrics. We'll talk about it a little bit, but really the triangle inequality is the only one that's hard at all in like almost all cases. And so the triangle inequality says, right, so I mean you draw your little triangle and you've got x to z, and basically if you go the long way around, well, then it's longer, right? So the hypotenuse, this is going to get you less than or equal to the distance of the sum of the two sides, right? So that's why that's called the triangle inequality. Out of curiosity, we can't have metric spaces for the imaginary plane. I mean, the imaginary plane can be a metric space. It's just that like a metric, right, like distance for us, you just have to have a different notion of what distance is, and it'd just be like a weird notion. So, like I and 3i, you could call them like two apart on the imaginary axis, but it'd be weird to say something is like I away from something else because we don't really have a way to physically grasp like what that distance means. So that's why we would like it to be a real number. Right, so like the distance we like to interpret as a real number, but like the x can be anything. Yeah, sure. Okay, so you're still, yeah. Okay, so 223, this was just showing that R is a metric space, which, again, that should make sense, and our metric on R is the distance is just the absolute value of the difference, right? So here we're not really concerned about which one is bigger. You just look at this gap and view it as a positive number, right? So you don't care if it's like y and x, you're still getting, or x and y, you're still going to get the same thing. And again, like the first two things are pretty much automatic, right? Like absolute value is always non-negative. When is it 0? If they're the same, all right, cool. Symmetric, yes, because the absolute value of x minus y is the absolute value of negative x minus y, and that's the absolute value of y minus x, right? So distance of x, y, from x to y equals the distance from y to x. Other interesting metrics on R? Yes. I mean, you can put like hyperbolic metrics, right? So I mean, well, that'd be more, you would want to consider kind of the upper half plane with like the hyperbolic metric, and like that's a way to get hyperbolic space. That's one of the models you can have. Similar with like the hyperbolic metric on like the Poincare disk, which is just a disk. But rather than viewing it with like the standard Euclidean metric, you could talk about, you know, straight line distance between points in the disk. Then yeah, there are other things. Yeah, so the other, like, yeah, LP norms. Yeah, there are a lot of metrics, and those are things you would talk about more, because when you're talking about like integrability and stuff in analysis, you would see a lot of these other metrics. And so the last one, so I saw some different arguments for this, and I just wanted to show you like the trick that maybe not everyone has seen before, because you haven't dealt that much with like showing that the triangle inequality holds. So I mean, one is to actually break it down into cases, right? And you just like look and you're like, okay, I can have x, z, y, or I can have like some ordering of these things. But that's a pain. You have to deal with cases. You have to think about it. And thinking's the worst. So the real trick here, right? So this is the absolute value of x minus z. So like, how do you suddenly get y to appear, right? Because you want to compare this to the distance between x and y and the distance between y and z. So you have like the common trick that you've seen a lot of places where you're adding 0 but in a nice form, right? So you can view this as x minus y plus y minus z, right? And then you can just break it up into the two pieces. And so like we know for real numbers that this is going to be true, right? So I initially had a typo there, but I said you could feel free to use this, and this is what I meant by you can use this. So right now we have, this is our A, this is our B, and so we have less than or equal to the absolute value of x minus y plus the absolute value of y minus z, and that is equal to the thing we want. So this important trick, okay? True. Yeah. What Mark says is also important as to why you care a little bit more in analysis about these different metrics than you do in topology. Especially, I mean, we're going to see today, right, that all three of these standard metrics, the Euclidean metric, the taxicab metric, and then the square metric or max metric, all give us the same topology on R2, right? But analytically, you're getting very different things there. And so, yeah, topology kind of, again, it's a little looser, and so you can have different things, seemingly different things give you kind of the same result. But yeah, this is an important trick. You'll use it a lot in triangle inequality stuff. I wanted to talk just briefly about these three metrics, right? So you guys have the definitions for like Euclidean, taxicab, and whatnot, right? So Euclidean is just like your typical straight line distance, right? So you would just look at this, and it's just, yeah, I'm not gonna, right, it's your usual distance formula between 2 points. So the first two, again, very easy, right? The distance between 2 points, it doesn't matter in which order you look at them because you've got the square root of the squares of things inside, right? So you don't care if it's y minus x or x minus y. When you square it, it's the same. Obviously, it's going to be 0 if they're the same point, and only if they're the same point. So it's like really the triangle inequality there that's slightly more challenging. And this is one where I would highly recommend, if you wanted to try to show it yourself, don't use the square root definition for proving the triangle inequality. I mean, I guess you can, but like don't work at, maybe that's not exactly right. How about I just say use vectors, use vectors for proving the triangle inequality. I mean, your norms in the vector space, I mean, it still relies on the square root definition, but you make your life a lot easier using linear algebra here, because when you talk about vectors, right, if you have x, y, and z, I mean, you can literally draw that triangle, and rather than have to like mess with things inside the square roots, you can kind of make things disappear by just thinking about like x, or x minus y, and so on. And the key is the Cauchy-Schwarz inequality, which you probably saw / proved in linear. I know like my classes did. I'm not sure if everyone saw that, but this just says in general that if you have a couple of vectors, say u and v, then the absolute value of their dot product or scalar product, whatever you called it, is less than or equal to the product of their norms. And so this kind of lets you show that the norm of the sum, right? So if you have u and v, then you can basically just view this is u up here, v, and then this is u plus v, and you can show that this is less than this plus this using the Cauchy-Schwarz inequality. And so that's the much easier way to prove this than trying to do a whole bunch of like algebraic manipulations inside square roots and stuff. It's a huge pain. So linear algebra is like very useful there. And then the other two are actually much simpler in terms of like proving them. They basically just rely upon where's the dot product there. The dot product shows up when, right, one of your definitions is that this guy is going to be the square root of u dot u. So that's where the dot product comes into play. Yeah, I mean, this isn't just like an immediate step. It requires some work. I'm just giving you like the key ingredients. I'm not proving this here. So this takes a bit of work. But essentially you start on this side. You take away the square roots, basically, right? You square each thing. You have this. You look at u plus v squared. You're going to get that middle term with like the 2 times u dot v. And then you compare that. It's going to be less than or equal to its absolute value. And then you can compare to the norms. And then you get the square of the sum on the right side. That's basically how it works. Yeah, and so then the taxicab, right, also referred to as the Manhattan metric, named after the Manhattan Project because it's a bomb-ass metric, or maybe just because people drive a lot of cabs in Manhattan. But anyway, this guy, right, you're just looking at... Don't give me a boo. That was great. Right, so this is like you're only allowed to drive on streets, and so you can only go, along the x direction or the y direction, but not in both directions simultaneously. And so you have things that look like this, and this basically boils down to using that trick again, where you add in, you do like the minus something plus something, and split it up. And basically that triangle inequality follows pretty quickly from that. And then the max metric, or the square metric, right? So here, you're just looking at the maximum distance between their x-coordinate, the maximum difference between the x-coordinates or y-coordinates, right? So if you have something that's like this, then their distance is going to be this distance because this guy is very small, right? So you would choose like this one, for instance, and then that would be their distance. And this basically, the triangle inequality, kind of boils down to the fact that, let's see, the max of a sum is going to be less than or equal to the sum of the maxes. Say AIs, BIs. Okay, so, right, so, yeah, that's going to mean nothing right now, but in analysis, what Mark said, these are known as the L1 and L infinity metrics. Has to do with, yeah, much more analytical focused things. But hopefully, some of you get the chance to take analysis. I'm not sure how much they would talk about it in first semester of real. I guess I saw that a lot more. They were at least like defined and talked about a little bit, but yeah, I saw a lot more of that in my second semester of real. But I guess your mileage may vary. I'm not sure what Mark's experience was. But yeah, this is like the key ingredient here, which makes sense, right? Like if you take a max first and then add them, you're only adding the biggest things, whereas here you have the max out of like all of the sums of things, and so you can have something smaller, if you're not adding the biggest ones in each. So this is just like a hint as to why these are metrics. The main reason I didn't have you prove them is, well, I guess I would have been giving you a large hint with this just to not make you take a ton of time proving the Euclidean distance, and I figured if you can understand what the picture is, that matters a lot more. It's not too hard to see that these should be metrics. Okay. So what do the pictures look like? What are the balls, right? So like Nick had that video that he posted. So, the epsilon ball around a point, I mean, we call it a ball because we're used to the Euclidean metric where it's actually a ball, right? So if we compare these, our Euclidean ball is literally a ball, right? So we get our little circle of radius epsilon, and we're happy. But then if we have the taxicab, our epsilon ball, no longer a ball. What is it? Yeah, it's a diamond. So why is it a diamond? Do we see like why that should be true? Yeah, I mean, so the super long way would be to just literally do all the 4 different cases of the absolute value. But yeah, kind of like your worst case scenarios are, okay, you just went all the distance in the y direction, or you went all the distance in the x direction, right? And that's going to give you these 4 points. And then all of the other ones will end up along one of these lines, because basically what you're looking at, right, is this plus this equals epsilon. And essentially, each of these turns into 2 cases, and so you end up with 4 cases, the plus or minus x, the plus or minus y, and they end up just being these 4 lines, and then you're only considering these segments because of the whole equals epsilon thing. So that's basically what's going on. For me, yeah, it's just like it's seeing these and realizing that like it's linear, right? And so you have to kind of just like connect the dots, and you're keeping your sum of absolute values constant along these lines. And then the square metric, surprisingly, is a square. So here, right, you're going up epsilon, back, epsilon, yeah. Right, so obviously these are all like centered at the origin, but like this is true anywhere. You would just shift this wherever you need to go, right? And again, this is hopefully not too surprising after dealing with that like -1 to 1 cross -1 to 1 kind of thing. Like it's really, yeah, the max distance you can go in any direction, right? But like you only care about the one coordinate at the time, and that's why you have like the whole line's worth at epsilon as opposed to just one point here. Because, you know, if you went back epsilon over 2, but you went up epsilon, like all you care about is the up epsilon part, right? And so you would get up here. So these are the good pictures to have in mind. And hopefully, yeah, these feel fairly comfortable. So one of the first questions you may ask is everything a metric space, right? So the key here is every set can be a metric space, but not every topological space is a metric space, right? You can't always talk about a distant, or, you know, if you want to keep the topology on your space constant, then you may not be able to have a metric on it. And we aren't going to talk too much about metrizability. There is like a brief part in our chapter, but we're probably going to skip it just due to time. But if you're just given a set, you can always define a distance on that set that will give you a topology. And so that's why I gave you 229. Yeah. I guess maybe we should first at least state 227. I didn't have you prove it, but right, we get a basis in any metric space, right? So if you have a space X with a metric D, then you get a basis of kind of what you would expect, right? So we saw it in R2, you get a basis out of the open balls. And so here, just to keep track of the metric, right, we're just keeping this as a subscript. And so you have all of the epsilon balls centered at points. And again, to show that's a basis, that boiled down to that one picture where, you know, maybe you have a point that lies in the intersection of these two guys, and the key is you can always find a ball centered at that point that still remains inside the intersection, right? And so what you were doing was using the triangle inequality and saying like, what's the minimum distance to like a side here, right? And then that would define the epsilon that worked. That was kind of our first real introduction to like a proof that required a lot of the triangle inequality. What's the radius of that ball? Yeah, I mean we went through that whole proof. The radius would be the minimum of the distance from, so if this is x, x1, x2, then this is going to be the minimum of the distance, or sorry, these need to have radii. So so this is the ball of radius r1 and r2. So it's going to be r1 minus the distance from x to x1, and then r2 minus the distance from x to x2. Right, so these are basically, I'm just saying like how far it's inside the ball, and then you're just tracking like how far is it actually from x1 to the border. So that these give you the distances of like the blue and red things. Because we have non-Hausdorff topological spaces, and all metric spaces are Hausdorff, thus not all topological spaces are metric spaces. Yeah. Yeah, with that specific topology. Yeah, exactly. Not infimum. These are 2 points. I mean, you have 2 things, so the infimum is the minimum. Right, if I just give you 2 numbers, like I don't need to take... They would coincide. You have a legitimate minimum. Okay. See some typing. Is x on the radius or the center? X on the radius or the center? What do you mean? Is x on the radius of what? X is the center of the new ball. So like the dotted thing is the b epsilon. I'll just say b of x epsilon. Yeah. Right. Yeah. Also true, Mark. Which is why that was not an if and only if statement. The only metric spaces are Hausdorff, but not all Hausdorff things. Yes, metric spaces are Hausdorff, but Hausdorff does not necessarily imply anything else. Okay, so given this basis, right, so the topology induced by this basis, which you can also refer to it, it kind of depends. Sometimes you'll see like the TD as well, where you're just like referring to the metric as opposed to the basis, but this is the notation we've had for like topology generated by a basis. So topology generated by these open balls is the topology induced by the metric. Right. And so this is what we mean when we say topology induced by the metric. A different metric could give you a different topology, right? You may have many different metrics, and as we're going to see for R2, these 3 metrics that we have defined all induce the same topology, which is the standard topology on R2. So how do we see if we're just given a set, right? So X is just a set, then I wanted to show you that this thing, which is aptly named the discrete metric, just says basically, right, the point, it has to be distant 0 from itself for it to be a metric. Equals 0 if y equals x, and is 1 if y is not equal to x. So basically, you are distance 0 from yourself, and you're distance 1 from everything else, right? Which is hard to draw, but yeah, this basically you're just really slamming all of your space. Everything is within, well, I guess the 1 plus epsilon ball for any positive epsilon, and it's called the discrete metric for a reason. The topology it induces is the discrete topology, right? So this induces the discrete topology on X. Sounds like the metric you would put on a complete graph. It's definitely a metric you could put on a complete graph. I mean, it would coincide with the natural path metric there, right? So yeah, on any graph, you have like a natural path metric where you're just like, hey, if this is one edge away from this other vertex, then they're distance 1, and if you have the complete graph, you have an edge between any two vertices, and so they would all be distance 1 away from one another. Yeah. So I guess it's not necessary that you would put it on it, it's that the natural one actually coincides with this discrete metric. Yeah, so basically, like, let's look at this statement. So it's nice in that you can consider any set, you can turn any set into a metric space. The bad thing about that is you're just turning it into that space with a discrete topology. So you're not really getting a whole lot of information most of the time, right? You're not able to really distinguish any points from each other because all sets are open. And so this really, there's no interesting behavior going on here. Sorry, different behavior between points. You can distinguish the points, but yeah, their behavior is all the same. And so it's not super interesting, but it is just nice to know. And so why is this true? Why do we get the discrete topology here? Let epsilon be less than 1. You can even let it be equal to 1 because it's the open ball, but yes. So for any x and x, the epsilon ball around x is equal to the singleton set for any epsilon between 0 and 1. But you can include 1 again, yeah, because the epsilon ball is the thing's distance less than epsilon away. And so if you consider less than 1, then you're still good. You would only get x in there. And so all our singletons are open. So it's saying if you have any point, go ahead, Nick. It does, but look at the metric. Like the distances are only 0 or 1. So like you don't get anything in that interval in between. Like the only distances possible are 0 or 1. Of the space, yeah. Right. Yeah, and remember, I mean, like the word discrete there is, I mean, yes, it refers to the topology and stuff, but like discrete also in the sense that like it shouldn't feel continuous in the sense that, yeah, you would have intervals, right? Like you're thinking you just have like points and then like this gap is 1, this gap is 1, this gap is 1, right? Like all of these are distance 1 apart from each other. Yeah, okay. So this isn't the only time we can get the discrete topology. So it turns out any metric, so you don't have to define the discrete metric to get the discrete topology. So the next problem, right, was if x is a finite set with metric D, then the topology induced by D is the discrete topology. So here, obviously, finite, very important. Why? Why is finite here? Why does this maybe not work for infinite sets? Like, what's special here? Or again, you don't even have to divide by 2 since it's strictly less, but yeah. But they don't overlap, right? Yeah, I mean, like, dividing by 2, basically it's the difference between, you've got, like, this point and this point, and this is obviously not completely accurate, but, like, whether you want this kind of thing to happen, like, there's, why? Right, like, there's technically no intersection here because these are open, but, like, they look like they intersect kind of thing. So, I mean, if you want to disallow that, then you can just do the divide by 2 or whatever, but, yeah, and obviously this picture isn't quite right from how this is defined, but, well, maybe it's the minimum from some other point, so this works, yeah. Right. Right, yeah. Yeah, what Devin said, yeah. Yeah, so it's really like this, and then this. That's the key. Yeah, and then the point is, these two guys are not actually, they're on the boundary, but the boundary's not included. Yeah. Yeah, and so this works, right? So just by this definition, and the minimum, right, the min exists because x is finite. So the issue would arise, right, where you need like the infimum. So if you had a bunch of things, for instance, if you had a sequence of points that were distance 1 over n apart for all n in the natural numbers, then this would have an infimum of 0. There would be no minimum. And so no matter how small you made your epsilon ball, there would still be points inside that ball. And so that would be the issue with the infinite part. Right. What's the equivalence between metric spaces? What do you mean, like the statement of 231? Or what do you mean by that question? Yeah, you have isometries. So things that like preserve the distance or something. Yeah. But yeah, for like the context here where it says like equivalent metrics, yeah, that's different, right? Like that's talking about the metrics being equivalent as opposed to the spaces. And so here it's just saying that they generate the same topology. But yeah, isometries between metric spaces would be the typical thing. So I don't think your memory is bad. Yeah, so I wanted to talk a little bit about 231 because it's not exactly the statement in 92. There's like a little bit of a difference, right? So here we've got T induced by D, T prime induced by D prime, right? Both on a set X. And then the claim here is that T prime is finer than T if and only if for each X in X there exists. So first of all, yeah, we should take a ball of radius epsilon, and epsilon greater than 0, there exists delta greater than 0 such that, let's see, so we want that to be finer, so we want the d prime thing. So the ball in the metric d prime, the delta ball around X is contained in the epsilon ball in the metric D around X. So, right, the picture is maybe you have your epsilon ball here in this metric, and then maybe you've got like balls that look like weird things in the other metric, right? So this guy would be this, and so you're looking for like, oh, this is what this ball looks like or something, you know, it's some weird looking thing. But, you know, if this is these are all delta, right, then this guy lies inside. Why is this different? Do you see a difference between this and 92? It's very similar, but there is a difference here in what we're doing. I don't know if anyone noticed or cared to look back since I said that 92 basically gives it to you. So we had yeah, kind of. Yeah, so the key, right, in 92, we had to consider any x in some b and show that there existed a b prime such that x was in b prime, which was contained inside b, right? But the key, yeah, exactly. It wasn't necessarily centered at x, right? It was just some ball that contained x. And so why is this equivalent? I guess maybe I should do open balls. Well, the point is, right, like, if you have a point that's not centered, well, you can then take a ball around it centered, or sorry, yeah, take a ball centered at it that stays inside the original ball. And so then you just reduce your case there. And so if you show that there's some B prime inside here, well, it's also inside the bigger one, right? So essentially, we recenter, and the result in 92 would follow. So that's all we're doing there, is saying like, okay, well, without loss of generality, because we could just take this guy inside that is centered at it, we just start with that guy instead, because life's easier if we just center at the same thing. Does that make sense? Because it does make the proofs a little bit easier, or the pictures easier to draw. Yeah, and I do think we ended up mentioning that at some point then, you know, similar to like, you know, we had a lot of these intervals where you have like an AB, like sometimes it's useful to know that like you can take a symmetric interval inside this, right? I don't know why I did epsilon without an X. x minus epsilon, x plus epsilon, and then, yeah, maybe you have like an a and a b here, right? Like you could take a symmetric interval inside if you need to. And so this is basically what we're doing here. We're just up a dimension. Okay. All right. So this is useful. So I didn't have you prove that, but that's basically what's going on there. And so 232 was to show that the product topology on R2 is equivalent, or is the same as the topology induced by the square metric, dm dt dm. Yeah, T is for taxicab. Cool, we're good. We had to use 92 here because R2 is not a metric space. R2 is a metric space. But yeah, I mean, they're saying the product topology on it. So yeah, you are using 92 here. Yeah, so 234 is more of the using 231. Or 233, sorry. Yeah. I agree. Yeah, so product topology here, I mean, yeah, do you guys want to explain this one? Doesn't it need a metric to be a metric space? Yeah. Well, I mean, yeah, it's metrizable, I should say. Yes. With the product topology, it's not. You can put a metric on it, but here it does not have it. Yes. Okay. So, yeah, we agree. Yep. Yep. So basically, yeah. Yep. So this already is an element of the basis for R2. Is so product is finer. Mm-hmm. Yeah. Right. So you just take like square of side length, minimal distance to an edge of the rectangle. Distance. Yep. And then this would give us that the topology given by dm is finer. So they're equivalent. Oh, side length 2 times, yeah. Yeah, 2 times. Yeah. Because the minimum distance is only here. Yeah. Okay, yep. So that's exactly right. So obviously, like, the reason we chose the square here is because of this piece, right? Like, this was very easy and nice. So it basically reduced it to just one case. And so then the next part, right? So 233 was to show that all of these metrics, the Euclidean, the taxicab, and the max metric, all induce the standard topology. On R2. No, we showed it earlier than that. This was way back. I don't know exactly when it was, but yeah, it was like when we first introduced bases, basically. 103. Yeah, so in 103, we showed open balls and open rectangles both generate the standard, right? So they give you equivalent things. So basically, what we just did in 232 showed us that dm induces the standard. So 232 implies dm induces standard. D obviously induces standard since that's literally the definition. And so, yeah, it remains to show that the diamonds are the same. And so here, I guess, did you guys have a preference? Do you like circles with diamonds inscribed or whatever? Or did you think the square was easier? Like, what did you use? Okay. Sounds good. So basically, right, by 231, it suffices to show basically you can do this, and then that you can, I'll just do it as a separate picture, that you can also do this, right? So, yep. Yeah. And I mean, you mentioned like 91. I think you meant 92, but like that was the point, right? That 92 basically gave us 231, and then this is just like the nice, cleaner result specifically for metric spaces. Yeah, so I mean, I think it's the same flavor, but this is the picture. So here, right, we're showing that dt is finer, and here we would be showing that your standard, or d, is finer. So what were your deltas, or did anyone find those? So, right, like this would be an epsilon circle out here. So here we have an epsilon ball in the Euclidean. Yeah, we can see that because, right, like these points are on the epsilon ball, and so you are taking the, well, still epsilon ball, but just now it's a diamond. Yeah. Yeah, so, right, like this is epsilon, negative epsilon, you're just taking the midpoint here, and you can find that distance, and so yeah, so delta is going to be epsilon over rad 2. Cool. Yeah, and you can do similar thing with the squares as well, and I think one of them ends up being like 2 epsilon or something, but yeah, that's the basic idea, and like these are the pictures, and it's clear you could find the delta, and then yeah, it's nice to also do it if you can. Any questions on that? So this is nice. This tells us that all of these metrics give us the same topology. So basically you can use whichever one seems most convenient for whatever you're trying to prove, right? Because we've often found that like rectangles are easier, especially when dealing with like products of things, than open balls. But sometimes open balls are easier when you just want to talk about, you know, things equidistant away in the Euclidean distance. What about the central hub metric? I don't think that's going to give you the same topology. But I haven't really thought about it. I don't know. Alright, so the one that we were talking about last night a decent bit was that the distance what? Yeah, like comes from yeah. So like the topology induced by the metric is like the topology created by this metric, or that comes from this metric. Yeah. I think that's a good way to think about it. Yeah. Mm-hmm. Okay. So right, and here X has the product, or yeah, box topology, and X has the metric topology induced by D. So I wanted to talk a little bit about what Nick was saying last night, and then I think there's another way. There are a couple ways to attack this one. So yeah, the notation was a little confusing, but I kind of figured out what he meant. So basically, right, it suffices to look at the preimage of an open interval, right? Because we're looking at preimage of open sets, and all of these, because the preimage of a union is the union of the preimages, it suffices to look at this guy. So we want to be a little bit careful here because, again, we didn't restrict this and say, like, subspace topology on the non-negative reals. So we have, like, a few cases, really. So, like, what if B is negative? What happens? Or, I guess, less than or equal to 0, really. No, I do want less than 0. Well, you get the empty set, right? Because nothing is going to have a negative distance. And then if A is less than or equal to 0, but B is greater than 0, then you're just getting, like, the ball of radius B around, I should say, let's look at a specific point first. So here you just get this radius B, and then if you have both of them greater than 0, then you're going to get all things distance less than B away, but you also, oh, yeah, no, that doesn't make sense. 4x in this. I did this horribly. Yes. What am I trying to say? Yeah. It's the union over these things. I had high goals here. Right. So D inverse of that's fine. Yeah, no, it's useless. Yeah, the issue is, like, it's the union of these things. I should have just done this from the start. Yeah, so in general, this is going to be the union over all x in x, or sorry, x in. I think this actually suffices, and then you just have to realize that sometimes this is empty. So distance from x is less than b, right? So what we're looking at is you've got a whole bunch of things. If you're in the preimage, then you're taking all things that are within b away, but you also want to remove the closed ball, right? Because you want things that are in the open band, and so you're basically taking away this stuff. So I guess now yeah, it's the open ball here, and so you want all this stuff in this, like, open band around it, and so it's the union of the open ball minus the closed ball to get the open thing here. So you want minus BD of XA bar, right? And so note that if B is less than 0, because you want to remove the closed thing so that you don't include this boundary. No. So think of it this way. Just think about what's happening in one dimension. So you have things distance between 0 and B is in the whole ball, right? This is giving you this. Distance from x to y is in here, implies that y, implies y is in here. And then if your distance, we want in in A to B, right? So if you have the distance here, you want to remove the closed one because you don't want things that are distance equal to A, right? So then this is in the closure of this, and we want the open from A to B, which is this guy minus the closed guy. The inner is open, but we need to subtract. Exactly, right, yeah. It is open here in the picture. We don't want to include that, but like to not include that, we have to include it in the stuff that we are taking away. Right, you have to subtract the closed endpoint at A to end up not having A in your end result. Is there a shell method? I don't think we're revolving things. Yeah, and so note that if B is less than 0, right, then like this is empty. And if A is less than or equal to 0, it's just open balls without any subtraction. Right? So that was the other thing I wanted to kind of point out, that you wouldn't have a washer if A is less than or equal to 0. It would actually just be a straight up ball. And then if B is less than 0 and is negative, then you just get an empty preimage. But like this works for everything, it's just that sometimes these are different sets. Okay. So just kind of wanted to point that out. Does that make sense? Okay. Well, then note that for all of these, right, this is open and this guy is closed. So the subtraction is open, right? We have intersection with the complement of a closed, which is open. And so this is open, and so D inverse of AB is a union of open sets. And so it's open. That's definitely one way to do it. Another way is to think of, alternate method. So here is just like take some xy in the preimage and show xy lies in its interior. Right, because if you can show that the preimage is equal to the interior, and Devin, you're probably going to say this is 191, or you use 191D, and like these are essentially the same thing, right? So basically 191D. Right, so that was a way to say, like, that was one of the equivalent things for being continuous, and what that basically boiled down to was, well, it is showing that the preimage of the open set is equal to its interior, and thus is open. So, yeah, the point here, right, is, well, in this case, the distance of x and y, just call it, I don't know, C. And this is in AB, right? Well, then there exists some positive epsilon such that C minus epsilon and C plus epsilon, this interval is still contained in AB. Then the epsilon ball around x cross the epsilon ball around y is going to land inside AB, because the distance here, right, like these are still distance less than epsilon from x, and x is more than epsilon away from A, and so this is still going to lie inside AB, and thus BD of x epsilon cross BD of y epsilon is an open containing xy and lying inside the preimage. So either of those would work. Can I draw a picture? Yeah. So this distance, so right. So this is x, this is my y. This distance is c. And then we're saying that, like, if I wanted to go from, right, like c is somewhere between A and B. And so then the point is you could have like a little bit extra around this, right? So you go to C plus epsilon and C minus epsilon, right? So like, let's just say this is C plus epsilon. Oh, wait, did I say? Oh, right. Yeah. And then this would be C plus epsilon from y. Maybe I should just do the epsilon. This is poorly drawn. Let's see. So, right, the point is, if you take a little epsilon ball around this guy, an epsilon ball around this guy, such that the max distance here, basically, give me another color. Right, so like the point out here over to this purple distance would be like C plus epsilon, right? Something like that. And same with like a point here to like a point in x. Basically, you're not going to get farther away. So this is still staying inside AB, right? You allow a little wiggle room from either of these points, but basically you didn't go outside the interval because you can do like the triangle inequality, right? So like if I have this as like z over here, then the distance from x to z is less than or equal to the distance from x to y plus the distance from y to z, which is c plus epsilon. And then this is going to be still in AB. Is basically what's going on there. And yeah, Devin, I think you got like a little bit more C plus 2 epsilon B greater than B. Do I need to do epsilon over 2? Oh yeah, I do need to do epsilon over 2 because I only assigned that. Yeah. Good point. Yep. Yeah. Good point. Yeah, because the real issue would be like some W over here. So this is less than or equal to, you just use the triangle inequality twice, right? So W to X, X to Y, and then Y to Z. And so then this would be epsilon plus C plus epsilon and here, now if we make it epsilon over 2, now we're good. Cool. Okay. Yeah, so good catch there. So those are both of those, and then I think this is quick enough. I want to just kind of finish here so that we can kind of start with the separation axioms next time. So y is a metric space Hausdorff? Because this one's pretty easy with pictures. Yeah, so this is the one where you just take like half the distance, right? So let epsilon equal distance from x to y over 2. Then x is in this ball, y is in the other ball, and these are disjoint. Cool. Yeah, so Hausdorff spaces, or metric spaces are nice. Sorry, what, Nick? Oh. Okay, yeah. Nice. Yeah, so I think I've mentioned a few times that Hausdorff is what's called a separation axiom, and there are several of these. And so we're going to kind of skip through metrizability, and we'll finish up chapter 4 probably next time, actually. And yeah, we'll see some things that are stronger than Hausdorff. We'll see some things that are weaker than Hausdorff. And I think here it's really important to just kind of like draw pictures, understand what's going on. And basically you have like T0, T1, T2, T3, and T4, which are these separation axioms. Hausdorff is T2. And so T3 and T4 are stronger than Hausdorff. T0 and T1 are weaker. And they all have kind of nice associated pictures, and it'll be nice to come up with some examples of spaces that like satisfy one but not another. And these give us another tool to tell the difference between spaces, right? So if one is T3 but not T2, and the other is T2 but not T3, and then the other one is T3, then they are not going to be the same space, right? They're not going to be homeomorphic to one another, given the metric topology. So that's kind of where we're going for next week. All right, cool. I will talk to you guys later.